Thanks, Martin, for the introduction, and also thanks, Martin and Peter, for inviting me to speak at this workshop. So today I'm going to kind of like describe to you a simple technique we call EMI testing that we have introduced about 3 years ago, and also our experience using this technique in finding a lot of bugs in GCC and LLVM. So the work is in collaboration with a few great folks from UC Davis. All of them at this point have PhDs already. And the work also has been funded partially by NSF, the US National Science Foundation, and also by Google. And here I also put a link here that has all the information that you can find about this project. And so let's start by, all of us here use compilers, right? So of, some sort. So we take a source program, and then we take a source program, and we run through compiler, we produce executable, okay? So as developers, we have a belief that the compiler should be faithful translators, the correct job. Now let's try to reflect on this trust, right? We want to say, how trustworthy are compilers and how they impact security and reliability. And some of you probably heard this public outcry from Linus a couple years ago, and after the release of GCC 4.9.0, claimed that GCC 4.9.0 seems to be terminally broken, okay? Because it's miscompiled Linux, right? Okay. So now let's look at, the kind of bugs. So what kind of real compiler bugs? So because as compiler developers, may have different notions from application developers. What is a compiler bug? So I classify them as 3 kinds. The first one is a real compiler bug. So this one is a bug from LLVM. And so this one has a struct that has 3 character fields, has a full function that takes a struct as a parameter and checks whether the C field or the E field to be 1 or not. If they're not, then abort. In the main function, there's a local struct, and then initialize all the fields to 1, and then sends this to full. If we stare this code carefully, and the code is valid, and it should run normally. Yeah. Okay. If you compile this with clan at -0, it's okay. -01, when you run this, you get core dump. Okay. So that's a real compiler bug because the program here does not have any undefined behavior. It's a valid piece of code. Okay. So this one is undeniably a compiler bug. So the developer who examined this and finally, after a few months, fixed this, said this is very, very concerning when I got to the root cause and very annoying to fix. And here's a link that's pointing to the bug report if you're interested. That's one type. And the second type is more debatable. So here I put quotes around the bugs. So now let's look at this GCC Bug Report 8537. If we look at this piece of code, and you see that there's a string here, password, that's confidential. Okay, it's a local variable. And then here we have this function. So this developer is very, very careful and try to wipe out this confidential information before you return from the code. But the compiler views this as bad code because this password here is a local variable. That means we return from this function, of course, it's going to be destroyed. So there's a lot of debate around this bug report. So, so this developer is very annoyed. He says, so to you all naysayers out there who claim this is a programming error or poor coding, yes, it is a bug. So at the end is the compiler developers resolve to be an invalid bug report. So it's not a compiler bug. That means the application developer should be more careful how to resolve this. That's one. And the next one is even more debatable. So let's look at this piece of code here. Again, here, the developer is very, very careful. First, it does a check to see whether the len is too long or not, okay? And this one is also kind of interesting. The developer is using a common user idiom in systems code to say whether you have, you have overflow or not, whether the len field is too long. So the assumption is if both plans len overflows, you wrap around, then this check should be okay. So try it as a clever way to detect whether you have a very large len, okay? Again, the compiler will reason, and to see this piece of code here is this one can never happen. The reason is because a valid piece of code should not overflow. So in that sense, this one check is going to turn this to 0. And that means this code is going to be removed. It's that code. And what's going to happen after that? Your code will suffer from buffer overflow. Again, this is not a compiler bug. Because the source program is relying on undefined behavior. Yeah? Now, our focus has been trying to find, the EMI testing technique has been focusing on finding real compiler bugs, the type 1s. So now let's, before I describe how to do that, let's think about, how many people know how complex is GCC or LLVM? You know, right? So it's really, really complex, okay? The code base of GCC is over 8 million lines of code, and LLVM is also close, I think, over 3 million lines of code. Very, very complex projects. So now the question is, if you have such complex projects, how do you find bugs in them? Okay. Not easy, right? So there's a very impressive piece of work from University of Utah called the C-SMITH project by John Rieger's group, that they have built, generate random C programs, try to crash the compiler, try to find miscompilations. And they did a very impressive job, try to avoid generating code with undefined behaviors. Okay? So the C-SMITH code base is actually quite complex with 50,000 lines of C++ code. So we want to do something different. Okay. So the C-SMITH approach is a program generation approach. What we want to do, we want to take a program mutation approach. That is, we have a lot of available programs already. Is there a way somehow we can mutate these programs in a semantic preserving way, then we can use all these different variants to stress test compiler. So that's kind of like our starting vision. But it's not easy. Okay. First of all, how do we generate these variants, these different variants, but also equivalent ones? Second, once you generate a variant, how do you know it's equivalent to the original one? Both are really hard questions. So we seem to get stuck. So here is the simple idea behind EMI. Okay, it's very simple to explain. So the idea is, why don't we try to relax the definition of equivalence, not with respect to all possible inputs, but with respect to just some chosen inputs. Let's say just one input I. And then our requirement is the variant should behave exactly the same as the original program on this input I, but for all other inputs, we don't really care. Okay? And the insight is we're trying to kind of exploit the interplay between two things. One is if you're given an input, given a program, we can run your program on this input. It's dynamic execution. So that's easy to know its behavior. And the other one is the compiler somehow doesn't know that we only care about compiling your program for this input I. It tries to compile your program correctly for all possible inputs. That's much harder. And let me try to use a picture to illustrate the idea. So we have the program P, that's a seed program. We have given the input I. We try to profile the run of program P on input I. And all the green nodes here are the executed ones, and all the red ones are not executed on the program run on this input I. Okay? And also we record output of the program run on P over I. And then what we're going to do is we take this information we're going to use that to produce a lot of variants of the original program P. So one thing we can do is we're going to keep all the green nodes intact, unchanged. For the red nodes, we can randomly delete them. We can insert some random garbage inside. As long as the program is still compilable, then we'll be good to go. So there's one easy property you see, that all the variants that we generate this way are equivalent to the original program with respect to the input I that we care about. That's clear, that's guaranteed. Now let's go back to the two challenges. Generation is super easy, yes? And also validation is super easy. Why? It's because you can just run any variant, compile this, run this on the same input I, compare the output. And that's pretty much kind of like the basic idea behind the approach that help us to find this gigantic number of bugs in GCC and LLVM. Okay. And let's go to the LLVM bug that I've shown you earlier. Let's see how we found it. So here is the seed program P that we used to find this bug. So this is the test program from the GCC torture test suite. And you can see the original program did not trigger anything. Yes? Okay. And also we noticed by doing profiling, all these abort statements here are unexecuted. That means they're dead. And then we produce a variant that get rid of some of the boards. And that triggered the bug. Of course, you may wonder at this point, what caused that? Yeah, keep that question in your mind. So that's the program that we were able to find to trigger that bug. But before usually we report, you can imagine this is a gigantic program. We need to reduce it. So here is the reduced one we reported to the developers. So let's try to understand what happened with this bug. So what happened is, first of all, there's a pass within LLVM called global value number, GVN, and says, now here you are trying to take this parameter and doing 3 character loads. Why don't we try to be smarter? Let's try to change this to 1 integer load, right? 3 loads to 1 load. Well, that's faster, right? But after doing that, there's another pass called scalar replacement of aggregates that, that's not right. Because by doing this, the original struct only has 3 characters. Now you read past the end of the struct. That's undefined behavior. But of course, it's a mistake the compiler made, right? Because the original code has no undefined behavior. But once the compiler made this mistake in judging the code that has undefined behavior, it says, your code is bad, I can do whatever to it. And in particular, it decides to get rid of these 3 lines of initializations. And now you have random garbage, okay? And that triggered the abort. So now this part is clear. But still, you may not be clear why the original C did not trigger the bug, and why the one that I showed you by deleting a few aborts, by deleting a few aborts, somehow triggered the bug, right? So what's the difference? Is it okay I ask the audience to participate a little bit? Yeah. Any guesses? Because it's always an interesting question to think about this. It's not easy. It took us a very long time to understand. It has to do with inlining. And the thing is, I think I showed so by getting rid of few aborts, the body of the f function is smaller. And then the compiler says, that's below the threshold of doing inlining. Let's inline the code. And somehow the inlining interacting with other things caused that compiler bug. That wasn't an easy discovery. Okay. Now let's look at the GCC bug. So this one, again, I want to make sure that we agree that this one has no undefined behavior. It's a valid piece of code. Okay? So just remind everyone that in C and C++, all the global variables, if you don't see an initialization, they don't get random values. They're initialized to 0. Make that clear. And then here the C is 0, so that means this inner loop here is not going to be executed. Yes? Okay. But now you see, look at this one, GCC-00 is okay, GCC-03, and the produce executable hence. So again, that's a compiler bug, that's a miscompilation. What happened here? It's kind of interesting. The compiler says, look at this expression here. B is not changed. Thus, it's a loop invariant. If it's loop invariant, we should try to move this outside of the loop, hoist. So it's going to hoist this outside and doing that. But by doing that, it introduced something interesting. That is, if B becomes -1, and so this, of course, is a magic number here, right? And then you do a -1, add 1 to it, you have an integer overflow. Again, the compiler says, that's bad, because your original program is invalid. Then again, I can do whatever to it. In this case, introducing an infinite loop. So the original seed is kind of like this. There was a B++. Again, the inner loop is not executed, so the B++ is also dead. Yes? So, but there is a B++, so this one is not a loop invariant, so it didn't do the hoisting. So that was the original program. We got rid of the B++. And were able to discover that bug. Okay? And so what I described to you is our first and the simplest realization of this EMI testing technique. We call that ORINE, and targeting C compilers. Only does random pruning of dead code. And the implementation is super simple, has like a few hundred lines of C++. That's it. And in about 11 months of testing, we reported about 200 bugs to GCC and LLVM. And so they confirmed at that point 147, they have fixed 110. And just want to clarify to everyone that fixing a compiler bug is not easy. Okay? On average, it takes about a few months to fix a bug in GCC and L. So now let's look at the kind of bugs we found. So most of the bugs are miscompilations, the most serious. Okay? And some fraction of them are crashing bugs, internal compiler errors. Some of them are compiler performance, not the kind of like generated executable, but the compiler is taking too long, or maybe runs into an infinite loop. And we did not focus too much on this part. So you can see the technique that the EMI somehow by design directly focusing more on the miscompilations. That's also evidenced by the bug reports that we have here. So at this point, many people usually have this question. Of course, you randomly mutate the programs, right? And also, I did not say earlier, so what we did is we focus on using the random programs generated by C-SMIs as seeds. So people say, yeah, you have random C programs from C-SMIs, you randomly deleting code from the random programs, then why should we care about all these bugs that you have found? Okay. And I guess we have a few answers. One is, most of the bugs that we have reported have been fixed. And also, if you look at the reduced test cases, many of them look very natural. It's very easy to imagine you write that kind of code. And second is, many of the bugs also critical release blocking. For GCC, they classify the bugs from P1 to P5. P1 is the most critical. A lot of our bugs are P1 bugs. That means if they don't fix such a bug, they cannot release the next version of the compiler. And also, some of the bugs affected real-world projects. There was an interesting GCC bug that we have reported, and then a few days later, another person reported bug, says, I'm trying to use GCC to compile media player, M player. And it was able to produce executable, but when I run it on a media file, it crashes. So, a few days later, they were able to trace it back to the original bug that we have reported. So that's ORINE. And since then, we have also gradually build two other realizations of the EMI testing idea. So one is called Ethna. So there is, so orange just prunes randomly code from the dead code regions. So Ethna also not only pruning, but also injects code into these dead code regions. And then there's the most recent one is, because manipulating the dead code regions is quite imaginable. So we say, can we try to do something with the live code regions? So that's the latest piece of work, which we're trying to mutate the live code regions, but still we maintain the EMI property. So let me just use some examples to illustrate. So that's the one where we're also going to insert code into the dead code regions. So here's a GCC bug that the original code has this one here, else c equal to 1, and then we added this one, replace that one by this one. And then that triggered a GCC bug. And how did we do that? Here's the original seed, and then the first thing is, it's a few steps. One is we get rid of that statement, we replace that by semicolon, and then we need to decide what to insert there. Okay? And what we do is we take code from the open source projects, grab kind of like snippets, and also from the original program seed that we grab snippets. And also we get the information of the required context that you have. So let me explain that with example. So for this one here, we say, yes, we have this particular snippet here. Yeah, if I in a break, that requires I to be an integer. So we want to insert this one into this place. We say, we need to find the integer I. What do we have? We have an integer h. Let's instantiate this I with h. That's what we're inserting. So that's the Ethna work. And this bug, again, is related to that GCC one. It's to do with loop invariant hoisting. Let me not spend too much time on that. So the third piece is Hermes, the latest one. We'll also try to mutate the live code regions. And that's not obvious how to do. So our idea is, why don't we try to take the program, run, and profile and record at each program point all the variable value information. And then we use that information to synthesize some predicates we know always true or always false. These kind of things are called opaque predicates from security. And we want to leverage these kind of predicates. It's easy for us to know, but given a compiler as a static analysis, it cannot infer this easily. And then also, by doing this, we want to ensure that we have no undefined behavior, and also we want to enforce the EMI property. Okay? Let me explain how we're going to do that. So here's the LLVM bug. Here's the original program that we recorded at this program point, some variable value information. And then we synthesize this gigantic mess. Okay? But if you stare at this long enough, you'll be assured this is still a valid piece of code. Okay? That triggered a bug in LLVM. Okay? So, and the mistake that LLVM made is judging this one to be always true. So that triggered a abort. Okay? And that was a mistake. Not always true, it's actually false. Because there's some difficulty to do with this sort of, you see all these operations, yeah? LLVM did not handle that correctly. So here are the three kind of things we insert. The first one is, here is always false predicate. Okay. And inside here, we can synthesize any compilable code. Because P is always false, we don't really care of undefined behavior, right? So that's the easiest kind. The second kind is, imagine you have already a statement S in the code already. We want to surround the code by conditional check. So we synthesize a predicate P that's always true. Yeah, that's also easy to understand. The third one is the most complex. That's used in the example. So we're trying to build some code that does some action. Yeah. So in that is, we want to save sort of, kind of like save some values, doing some backup, and then we recover here. And I guess the details are not that interesting. Okay. The challenge here is how can we build these valid expressions here that don't have undefined behavior? Have to make sure that's the case. Here's how we do that. We do that using a bottom-up process. Here we have the state information of the variables, and also we use a work list procedure, and imagine that we want to use BCEF as the 4 variables. We want to build a valid expression out of it. So first, we try to say, let's build an expression, binary expression, using 2 variables. We take B and E, and we try the operator divide, but because E is 0, we say that's not good, that's invalid, so we should try something else. Okay? And then we decide to try C and B. We want to use this Boolean AND, that's valid, and we keep it. We push this onto the work list. We continue our process. At the end, we generate a valid expression. Okay? That's a very high-level description of the kind of algorithm behind Hermes. So, and we, I guess, kept up our testing effort over the last 3 years. Till very recently, we have 1,141 bugs, and out of those, 636 have already been fixed. So here I want to clarify that every one of these 636 bugs fixed, every one is unique. No duplicates. Every one is unique. Each one is pointing to a unique bug that they have fixed. Yeah. If there's a duplicate, the developers will be very eager to mark it as duplicate. These are all marked as fixed. Yeah. So something I just want to briefly, there's some additional effort that we have done. One is work at Easter 2015. We also stress test the link time optimizers in GCC and LLVM and found a bunch of bugs there. And also very recently at ICSI, we also try to analyze the compiler's diagnostic support. That is, does it give correct warning messages? Because the warning messages can be very important to the application developers. So there we also found about 100 bugs also. And the most recent effort is a effort that tries to move from testing to bounded compiler verification. That is, somehow if we limit the size of the program we want to generate, okay, if you can somehow enumerate all these possible programs, then you can get some bounded guarantees. So that's in this recent work that we have done. By doing this, so what we did is we take all the GCC test suite, the small test cases, and we try to find all the possible ways the variables can be used and instantiate the program this way. So that means for each one, we generate a lot of variants. And by doing this, we were able to find a lot of additional bugs in GCC and LLVM. And most importantly, we're able to find the first effort to find bugs in the C++ front ends of both compilers. And that's probably not surprising to people because the C++ front end is very, very hard to get right, especially to do with C++ templates. So here are some ongoing efforts. We also want to extend EMI to handle floating point code. Conceptually sounds easy. It's actually not quite that easy because for integer programs, the result here is very clear. If you get a value 0, you should get 0. But floating point code, that's not clear. How do you even build an oracle? Yeah. We have some ideas, but need to do the serious work. Okay. The other one is adapt EMI to other languages and settings. What we have done is we have also looked at JVM and some various other languages. Right. The last one I mentioned is try to support bounded compiler verification. We have done kind of like the second piece of work. The first piece is we're going to have is kind of like according to a language grammar, we're going to generate up to a certain bound the token sequences. And from the token sequences, we can enumerate all the possible programs that you can have. So we decouple this into 2 phases. We have done the second phase. We need to kind of like combine that with the first phase. And at this point, many people probably also want to know, how about CompCert? How much time do I have lost? 10 minutes, okay, that's plenty. Yeah, ComCert. So for ComCert, of course, everyone knows what's ComCert, right? It's a verified compiler, very impressive project. I think it's already a decade long. And over the years, we have done some sporadic testing of ComCert. And I guess in August, I spent 2 extensive weeks trying to test ComCert. Okay, so let me tell you my experience. So here's something that we found very early on during the sporadic testing. Look at this piece of code. It's garbage. Okay? And ComCert view this as okay. And the reason is probably not very clear. It's clear that this garbage code, right? Because you have array and then you initialize with a scalar 0. What happened is ComCert views the array initialization in this way. Turns into multiple initializations of scalar things. Right? That's a little oddity of the compiler. Nothing really serious, because the original program is a bad piece of code. Nobody cares. Right? This one is more interesting. Okay? And initially, I thought we found a bug, a serious bug in the compiler, but turns out to be not very serious. It's something front end. So look at this character literal here. I want to maybe ask folks here, do you know in C programs, if you have a character literal, how many bytes does it have? Of course, the obvious answer is 1. That's not right, yeah, and that's 4. It's size of int, okay? So ComCert earlier mishandled that. Give the output 140, but then the value, because the int should be sign extended, so it should be negative, okay? Nothing really serious. It's really just an issue in the front end. Okay. So how about this one here? So this one is an internal compiler crash of ComCert that we found very recently. This code here, I just want you to stare at this for a few seconds. This is a completely valid piece of code. Yeah, nothing wrong. But, get a fatal error from ComCert. Okay? Again, a crash is not a big deal. Yeah. So this one is more interesting. So for printf, there's a return value also. It returns the number of bytes you print. And if you look at ComCert 2.6, interpret this piece of code, somehow that value t, you still should be true, but you still get 0. That was kind of like noticed very recently. Really cracked it. Initially, we thought was some errors in the reference semantics. And that would be much more interesting. It turns out to be in the ComCert interpreter's emulation of the built-in functions, printf. So this one is very interesting. This is a very ugly piece of code, but just believe me, it's a valid piece of code, although ugly. And this one is interesting, led to a crash in the regis allocator of ComCert. Okay, we found a bunch of those. So I guess that's kind of like our experience in ComCert. We found about 30 also crashes and some little oddities in the compiler. Nothing serious in the verified component, so very impressive piece of work. So maybe that also means we should find better, other ways to find, to test a verified piece of software. Yeah, so just want to quickly recap. So, the EMI technique is a very simple, it's generally widely applicable methodology. You can use the test compilers, you can test, suppose you like to build static analysis tools, you can use it to test your static analysis tools. And it generates real-world tests. That means we guarantee every bug we find is a real bug, no false positives. We guarantee that, okay? And also requires no reference compilers. So that's very different from, like C-SMIT's type of differential testing. And our realizations are very effective. Over the last 3 years also, we have found a lot of bugs. And many of them are long-latent and miscompilations. I think yeah. I think, testing compiler is fun. And of course, there's always this question is, can you find the next 1,000? Sure, you can always. So that's why I think it's really important to be able to do some bounded verification. Our kind of like next effort. With that, I want to thank you for your attention.
That compilers exploit undefined behavior, because that's almost always not what the programmer wants, right? I would like to see an error message or maybe a compilation that tries to stay as close to as what I probably intended, not just say, oh, the programmer made a mistake, so let's exploit that in the worst possible way.
Yeah.
So if you, how many of the bugs you found are due to some undefined or asked differently, if you use the proper programming language other than C or C++, how much of these problems will still be around?
Okay, that's a good question. So I want to clarify a couple of things. One is, all the test cases that we have found to report bugs, they don't have any undefined behaviors. Everything is valid. Because otherwise, the bugs you reported, the developers were very quick to tell you, you're wrong. They're not bugs. Every case here, although in the inside, maybe there's a bit has undefined behaviors, but the whole program has no undefined behaviors. And I agree with you, Peter, also, it would be nice the compilers would be able to give some more meaningful error message to say, yeah, maybe you have something, a fishy case, right? You want to take a look more carefully. Yeah, so the error reporting, the warning messages can be better. Sometimes they do a reasonable job. Some cases they cannot do. But again, all the programs that we have are valid piece of code.
So what do you do if your input and your program and your program has non-determinism? So in that case, you will report false positives.
Okay. Excellent question. So this is about one assumption that we made, is that the seed program on the input I, the behavior is fully deterministic. Now the question is, how can you extend this to concurrent software and all that stuff, right? Yeah.
Programs can have non-deterministic behavior.
You can have, yes, you can have some random values and all
Which is
that.
defined, but not deterministic. It's just like...
That's right. Yeah, so first of all, we have to somehow determinize such an execution.
I'm wondering, once you start with the deterministic code where you modify or mutate the step code, how long does it take this procedure? Do you actually get something meaningful?
That's a really good question. Yeah, so that's something we have been thinking about. That is, maybe there's some seed programs, no matter how hard you mutate, right, and it won't lead to anything interesting, right? How can we somehow decide a priori that a seed is going to be promising, another is not going to be promising? We don't have any good ideas. Of course, one thing is anything you don't have a good idea, you can use machine learning. No, so we do have a lot of test cases. We can try to mine some features. We can try to build a model. Maybe that help. But at this point,
cases like pre-generated, like written, or you also somehow generate those deterministic programs as well?
Oh, so the programs that we use mostly are from this C-Smith random program generator. Okay. And also, we did use some open source projects as well. But one big issue using open source project is once you find a bug, especially a miscompilation, how do you reduce it to something small that you can report? And that's a problem nobody has a good answer to. Okay.
Well, there was someone in here.
Yeah. Maybe it's not quite related to miscompilations, but have you also discovered performance bugs? Meaning that you mutate a C program and then you feed it to the compiler and it takes a couple of minutes to compile. Right?
Yes, we did. I think from the first realization of EMI called ORI, there was we have a table that 19 of the bugs are performance related. Sometimes maybe at -01, it takes like very quickly 1 second, and -02 suddenly becomes an hour, or even longer, running into infinite loop. One issue with not finding more of those kind of bugs is reducing them is not easy. We don't have good ideas, and nobody has good ideas how to do that. Okay.
How far do you get with bounded like the bounded verification? What do you want to do?
I'm
How
sorry?
far do you get with this bounded verification?
What we have done is we have a system, we call this a skeletal program enumeration, where we are, if you give me a program skeleton, for example, a test case from GCC test suite, we are able to enumerate all the possible different variable usage of the same program. We only change the variable usage, nothing else. By doing that, we found 200 to 300 also bugs in the front ends, and we still have.
You got a question?
No.
Okay, it was involved.
So following up on the sort of skeletal programming enumeration, do you have some sort of template or specification that you're using for enumeration?
Nothing really. We just. Yeah, there's no test case we have, and then just try to enumerate all the possible combinations. Say, how can you enumerate all the possible compilable tools, or type correct tools, and that's something that we hope to grow in the future.
Okay, I think no more questions, so let's thank Zhendong again. So there is lunch now, waiting, we'll meet in